Okay, today is 12/6. Happy Santa Niklaus-Tag. So, first ionization energy is the energy required to steal which electron, do you suppose? This is like Grant's tomb. First ionization energy is the energy required to steal the first electron. You can steal more than one electron from some elements. Some elements will actually give up 2 electrons, but the first ionization energy is the energy it takes to get that first electron off. So this is first IE, first ionization energy. And mind you, we don't have a scale here, so we'll just sort of assume that, does lithium, what does lithium look like? Let's remember what lithium looks like. So there's lithium. Two energy levels. It's on the second period. 1, 2, 1. Is it very hard to get lithium to give up that outer electron? No. It's got a single stupid electron hanging on the outside. If it ditched that electron, it would look just like helium. It's HERO. So perfect. So the first ionization energy for lithium is pretty low. And as I said, we don't have a scale or anything, but, just in relative terms, it's the lowest thing. It's the lowest ionization energy in its period, because group 1 always has Gesundheit, the lowest ionization energy in its period. It's the easiest. If you're going to bully somebody for their electron, insert lunch money here. If you're going to bully, this is the easy target. Group 1 is the one that's going to give up the electron without a fight. So what if we now move over in that same period, and what element are we talking about now? What's next? Same period. Beryllium. Beryllium. And beryllium, of course, has 2 electrons in that outermost energy level. Would you say that beryllium has a higher or lower ionization energy than lithium? What? Higher. It takes a little bit more energy to strip an electron from beryllium. Okay. So if we moved over in that period, we would have boron, carbon, nitrogen, oxygen, fluorine, and neon. Boron higher or lower than beryllium? Higher. Yeah, because what happens to ionization energy as we move across the period? It increases, and carbon a little bit higher, and nitrogen a little bit higher, and oxygen a little bit higher, and fluorine a little bit higher. And then we get to neon. What do we know about neon? Totally stable. Not interested. Not interested in giving up electrons. Neon, and every noble gas, has got the highest ionization energy for its period. Okay? Absolute highest ionization energy we would find in that period. Now, if I were to sort of shrink this and make it part of a larger picture. So within a period, we know that we're going to see that kind of trend. We're going to see the ionization energy climbing as we go. I lost the top of my fluorine. Whoops. Well, if we go down to the next period, what would be the first element that we would be looking at? Sodium. And actually, let me move these up just a tiny weensy bit. Sodium. So, comparing sodium and lithium. What do we know about the differences between sodium and lithium? And I'm going to make this a sodium atom here. So 1, 2, 3, 4, 5, 6, 7, 8, 1. Would sodium have higher or lower ionization energy than lithium? What would it be? Lower. A little bit lower. Takes even less energy, and I could actually remember these are all relative. We have no absolute scale here. So it would be a little bit lower than lithium's. Well, what comes after sodium? Magnesium, and then aluminum, and then silicone, and phosphorus. And what's going to happen as we go? Why, each time they're going to go up a little bit more. And when we get to, let's see, chlorine, argon. So they go up a little bit, and then where's the big spike occur? When we get to the what? Which member of each period has zero interest? The noble gas. And that's going to be our big spike. And actually, I should probably move all of these down just a tiny bit. And remember, this is all relative notions. We don't have absolute values here. But if we were to do a little sort of, fourth grade connect the dots kind of graph, what would we see? What would we see? Well, we would see this. Boom. What do you think would happen when we went down to the next period? I like making sound effects when I graph. Boom. And then what would we see in the next period, do you suppose? Hold on. Okay, so without plotting names or any kind of specific values, what would you expect to see in the next period? Boom. Boom. Love making those noises. Yeah. Every single time we get to the end of a period, and we're going to hit the peak. So every time we hit the end of a period, when we hit noble gases, we're going to hit that peak of ionization energy, and then we're going to drop dramatically when we get to the start of the next period. Because group 1 is always the lowest ionization energy in its period, and group 18 is always the highest ionization energy in its period. And you're going to notice, if we circle, here's group 1, period 2. A little bit higher than group 1, period 3, which is going to be a little bit higher than group 1, period 4. And then I kind of run out of axis, but, it's not supposed to be that way. Those are going to keep dropping. These are going to keep dropping. So if we drew a straight line between these, it would be downward. A straight line between these, it would be downward. Every group is going to be a little bit higher in ionization energy than the group next to it, and every member of a group will be a little bit higher in ionization energy than the member of that group that's directly below it. Now, what if, because we're wild and crazy kind of critters, what if we decided that just for grins and giggles, we were going to, on the very same graph, this is madness, I tell you, madness. We were going to graph, again, with no absolute values, but really just sort of general impressions. We were going to graph atomic radius. So for lithium, and we'll put atomic radius up here. So atomic radius. We don't usually abbreviate that way. Let me get rid of that, and let's just put radius. Okay. So lithium, atomic radius there. Would beryllium have a larger or smaller atomic radius? Slightly smaller. Would boron have a slightly larger or slightly smaller atomic radius than beryllium? Slightly smaller. Would carbon, the next one over, have a slightly larger or slightly smaller atomic radius than boron? Oh, gee, slightly smaller, slightly smaller, slightly smaller. Boomf. What's that? So we get to neon, smallest in its period. What do you think happens next? Because when we go to the next period, to sodium, and actually I need to move these down just a little bit. When we go to the next period, when we go to sodium, what are we going to see? What's going to happen to the atomic radius? We've added a whole energy level. It's going to go up. It's going to go up. And is sodium larger or smaller than lithium? Little bit larger. And then we're going to see that same darn thing. Oh, look at that. And then what will happen next? Gee, the suspense is killing me. So what do we get to do? We get to make sound effects. Yay! So we go. Isn't that beautiful? It's a little bit like an inverted Christmas tree if you turn it sideways and think about it really hard. You know, if you're prone to that sort of thing. This illustrates really nicely. They are inverse trends. And I noticed a lot of people on the quiz yesterday for describe the relationship between atomic radius and ionization energy. What's the basis behind both trends? So most people could get that it's an inverse trend, that they are inversely proportional. As ionization energy goes up, atomic radius goes down. As atomic radius goes down, ionization energy goes up. That's the easy part. The harder part for people, I found, was explaining why that happens. And if you're one of those pain in the tuchus people who likes to know why things happen, I think it actually is, like, I can't just remember trends. I have to understand why. The basis behind both trends is that the ability to hold on to outer electrons tightly dictates how much energy is needed to remove them, and it dictates how tightly the atom can condense itself, how tightly the electron cloud can be condensed. So atoms that are holding on very, very tightly to their outer electrons, that have minimal, what was that term we used when the electrons are shielding the outer electrons? What was that? Electron shielding. That's it. When you have high levels of electron shielding, it's hard for the nucleus to exert a good tug on the outer electrons. So you end up with a very fluffy atom, and you also end up with an atom that isn't, again, it's fluffy. It's not keeping a tight grip on those outer electrons, on those valence electrons. They get removed easily. It doesn't take a lot of energy to pull them off. Okay, good. So, does that seem clearer? And I like the visual. Like I said, I don't understand things without visual representations of data, so I think this is a good way to look at it. There's an actual graph, presumably with actual values, and this is atomic radius, and this is ionization energy. And hey, looky there. Zoop, boom, zoop, boom, zoop, boom, zoop, boom. Love making noises like that. And down here, with the radius, zoop, boom, zoop, 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 with a few weird little exceptions. I am not sure why, actually, sulfur is a weirdo, but it is. I'm sure somebody knows, but it's not me. Sulfur, it's a freak. Every time we have a low point in ionization energy, we have a high point in atomic radius. So a great test question, which I haven't asked before, but I'm realizing as I look at this, it would be fantastic, would be to look at a graph like this and say, identify the group represented by the circled elements with no labels of elements on it. So if that's ionization energy, the high points would be which group? Vote with your fingers. That just means hold up the number of fingers for the group. Like 1, 2, 18. Have to take off your shoes. Highest ionization energy in their group would be what? I don't know. Actually, okay, I don't know how you're going to vote with your fingers on this because you do have to take off your shoes. What's the highest ionization energy in their period, rather? What group? Who's going to give you the biggest fight about taking their electron? 18. Those are noble gases. So when you see those peaks in ionization energy, you go, oh, well, that's easy. That's the noble gas because there's no way they're giving up an electron. Totally happy. Not going to happen. When you see the low points, the other question would be, what group is represented by those circled elements? It's the lowest ionization energy in their period. What would that be? Group 1. Yeah. Okay, so now let's talk a little bit about stealing a second electron. Stealing a second electron. So, subsequent ionization energies. You can remove a second, a third, a fourth electron from some elements. But every time you remove an electron, it gets harder to take the next electron. So, again, to go to the lunch money bully scenario, once you've had $1 taken from you, you're probably going to protect your other dollar a lot better. When you remove an electron from a positive ion, you're facing an uneven tug of war. Okay? Let's look at why that is. Okay, so there's lithium. It's got 3 protons pulling on 3 electrons, exerting force on 3 electrons. When we strip 1 electron from lithium, what's the tug of war look like now? We have 3 protons exerting an attractive force on 2 electrons. It is much harder. Now, in this case, lithium will not give up a subsequent electron because it's reached noble gas configuration. It would take a tremendous amount of energy. Let's look at its neighbor. What's its neighbor? Beryllium. So beryllium has 4 protons. And to start off with, beryllium is sitting there with 2 electrons on the outer level, 2 on the inner level. It's got 2 valence electrons. 4 pulling on 4, even tug of war, evenly matched. It's not crazy hard to get beryllium to give up an electron. Okay. First ionization energy. A little bit harder than lithium, but not a terrible struggle. When we go to remove that second electron, it's not a fair fight. You have 4 protons exerting a force on only 3 electrons. They are holding on to that electron more tightly. Now, in the end, typically beryllium does give up that extra electron because it gets it to a noble gas configuration. But the energy required to rid itself of that second electron is higher than the energy it took to pull off the first electron. Now, for both of these, so here's lithium, here's beryllium. What do they look an awful lot like now? Actually, they look just like somebody else in terms of electron configuration. Helium. They've now reached noble gas configuration. Ain't no way you're not going to get an electron off of something that's reached noble gas configuration. So if we look at ionization energy, And let's again do sort of a very generalized graph. So if we look at lithium, IE, so this is the ionization energy required for lithium. We'll say first IE, second IE. Well, first IE is here. Second IE is somewhere up here. It's crazy high. Why is it crazy high, Lucas? So why is lithium's second ionization energy so high? Well, you know what? Maybe. Oh, go ahead.
In noble gas.
It's now reached noble gas configuration. It's not going to give up another electron. If we look at beryllium, which commonly gives up 2 electrons, first ionization energy. Well, the second ionization energy is higher. Guess what happens to the third? Woo! Off the charts. Because so 2 things have happened there. You've got an unevenly matched tug of war. You have, in beryllium's case now, 4 protons pulling on 2 electrons. But you've reached noble gas configuration. You're stable. That ionization energy is through the roof. It gets really, really high. Questions? Does that make sense? Okay. So here's the takeaway. Subsequent ionization energies are higher. And when you see a crazy spike, when that ionization energy goes through the roof, you say, oh, hey, look at that. It's got to be a noble gas configuration. Because it's very difficult to remove an electron from something that has reached noble gas configuration. Okay, and IE in groups. We kind of already talked about this when we were graphing. The farther out from the nucleus, the more sort of unguarded you are, the easier it is to pluck electrons off. Again, we have that term, electron shielding. And it's the same thing that makes those radii larger, makes it easier to, lose electrons, because they're so far out from the influence of the nucleus, and they're so shielded by multiple layers of other electrons. Okay, so I have 3 elements here. So I've got lithium and sodium, which share a group or period? Group. I've got lithium and beryllium, which share a group or period. Period. They're in the same period. They're both in period 2. And we know that group 1 tends to give up an electron pretty easily. They've got the lowest ionization energies in their period. They'll practically throw their electron at you in passing. I mean, it still takes some energy to remove it, but it's easy to do. So when lithium gives up that electron, what we now have, and I'm going to move you over. Yes, I'm talking to my drawing. It's okay, it happens all the time. Darn it, how did I do that? What we now have is a lithium ion, a lithium 1+, and it's shown as Li1+. So here's my question for you. Would that change lithium's radius at all? So we said that when we strip off the first electron, that first ionization energy, it's much, much harder to strip off the next electron, because now the nucleus is able to grip those electrons more tightly, metaphorically speaking. Would that change its radius? Does how tightly the nucleus grips the outer electrons have anything to do with radius? Oh yeah. Oh yeah, sure does. So now the lithium 1+, the radius, is actually going to decrease a little bit. So have we talked about the term cation yet? Okay, so an ion is a charged atom, and there are 2 kinds of ions. There's a positive ion, and that is a cat ion. And the mnemonic that I have been using for the last 25 years is, cats are nice. Purr, 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 purr. I'm not particularly a cat person, doesn't matter. It's a decent mnemonic. I prefer dogs. But Cats are positive. I have positive thoughts about cats. Cations are positive ions. So, cation formation, as a rule, does what to atomic radius? Okay, so cation formation does what to atomic radius? Increase or decrease? Vote with your thumbs. Increase or decrease? Cation formation decreases atomic radius. Cations tend to be just a little bit smaller than the neutral atom from which they were formed. This was a question that was on your quiz yesterday that I told you all to skip because we hadn't talked about this. This is what I realized. I realized that we hadn't talked about this. So, cation formation decreases atomic radius. Let's look at let's look at the elements and ion that we had in number 8 on your quiz yesterday. Okay, so let's arrange these in order. We'll do decreasing order. Largest to smallest. They're all in the same period. So we're working on atomic radius here. What would be your where is your largest element in a period found? Which group? So what is our largest element here? Sodium. So we have sodium. Now, I'm going to leave out the ion for a moment. And just like when I give you the tricky ones where you've got everything in one group or everything in one period plus one that's from a different group or period, do the things that are in one period first because they're easy, and then you can figure out where the ion fits in. So what's going to be the smallest element in any given period? What is it? The noble gas, group 18. We don't have a noble gas for this one, but we have a group 17. So that would be the smallest that we have. So then it's a simple matter to put these in order because it would be, what? Aluminum would be a little bit bigger than chlorine, and then we would have magnesium. So the only thing we have to figure out is sodium. Is a sodium cation larger or smaller than a neutral sodium atom? Slightly smaller. So we would go ahead and tuck our sodium 1+ right in there. Not too bad. Now let's talk a little bit. We're going to start to talk now about the process of making anions. If you are anti-anything, I am anti-raisins. I think they're an offense to humanity and civilization. They should be illegal. But, you know, what do I know? We're going to start to talk about anions. Anti, these are what kind of ions do you think? Negative ions. So this is called electron affinity. And there are atoms which accept an additional electron. When we add an electron to a neutral atom, we make a negative ion, and what we call it, it's so weirdly put, but it's just weirdly defined, we call the energy change electron affinity. So, if energy is released when the atom accepts the electron, EA is negative. If energy is absorbed, EA is positive, and positive EA ions are totally unstable. So, we said that a cation is when we steal an electron from an atom. If we have an atom that takes on an extra electron, it now has a negative charge. It is now an anion. That is a negative ion. So when we create an anion, there are some atoms that are willing to accept an electron. And what group would tend to accept electrons to get to noble gas configuration? 17. 17 is the classic example. Now, we can make anions out of group 15, group 16, but group 17 are the easiest ones to talk about because they are the eagerest to accept an electron. Okay, so here we have fluorine. It's got 9 protons pulling on 9 electrons, and 7 of those electrons are on the outermost energy level. So it's got the smallest atomic radius, almost the smallest atomic radius, I should say, in its period. And it's totally not unwilling to accept an electron. As a matter of fact, it's not very stable until it gets that electron, because it wants that electron so desperately. And this is where I like to think of chemistry in terms of analogies for life. Sometimes if somebody wants something so desperately, they're not real stable about how they get it. And you may have seen this in your friends or family or yourselves at some point, you know, like, I must have that cookie. I will do anything. Ooh, that kind of hurts my throat. Fluorine desperately wants an electron. It will stop at nothing to get an electron. So it's not terribly stable. Now, and I'm going to do the electron that it picks up in a different color just to highlight the fact that it got one. Once it gets that electron, it's much more stable. And as a matter of fact, its overall potential energy is lowered. It has less potential to do something crazy because it's stable. So if we were to draw this on a graph, because you know I'm all about the graphs. All about the graphs, all about the graphs. We could say that, I'm going to shrink that just a little bit. This is potential energy. And fluorine, with its 7 electrons, is fairly unstable. It's fairly high energy. If we look at what happens to fluorine when it accepts an electron, and we'll draw it down here with 8 electrons, its energy drops significantly because it's more stable. You can think about this as a rock on a hillside. How many of you have driven down Route 7, down towards Steubenville, down towards Wellsville, down along the river? And there are those signs that say, caution, falling rocks, and every now and then one does. Rocks that are not attached to the rest of the cliff face are not real stable when they're sitting up on a hill. That's the situation we have here with fluorine. You know, it's sitting up on this rather steep hill, not stable at all. Once it gets an extra electron, it's essentially hit Route 7. It is now stable. It's not going anyplace else. It's done. It's lowered its energy and it's become more stable. So here's the cool part. We can visualize the amount of energy that this has as sort of a bar graph. And I'm going to switch colors yet again just because I can. So if its energy before was here, and its energy now is here, and we'll put our little fluorine here and our little fluorine here, there's a difference in the amount of energy before and after. There's the energy before, there's the energy after. Well, where did that energy go? Because energy can't be created or destroyed. Where does that energy go? Where could it go? What are the options here? Into my gas tank. There's energy in my gas tank. Into my cells. There's energy in my cells. Into the heart of the TARDIS. There's energy there. Watching for recognition. Nope. Okay. Into a nuclear fusion reaction in the heart of the sun. Where could it go? Where could this energy go? It's just given away. Poof. Here's a little bit of energy. Out into the world, out into the universe, out into the environment, out into whatever fluorine is hanging out next to. Poof. Here's some energy. The difference between this high energy, unstable condition and this low energy, stable condition, that's the electron affinity. And as long as the thing that has taken on the electron has a lower electron affinity, we call this, it's a negative electron affinity. It's a negative EA, because that energy goes out into the world. So, and these are numbers that mean absolutely nothing. I want to warn you in advance. If the energy here is 100 and the energy here is 10, the difference is negative 90. Does that make sense? So the electron affinity is negative. So it's more stable with that added electron. Now, let's think about the other case. Okay, so here we have a sodium 1 plus ion, sodium ion, Na1 plus. This has already given up an electron. It's already shed one electron so that it looks like neon. What if we wanted to force it to take an electron? What would happen to its potential energy? Would it be more stable or less stable? It would be less stable. So if we took our little friend sodium here, and we, the image that I want you to have in mind is pressing a spring down with your thumb. Maybe we need to find some springs to do that with. If you are to push that electron onto the sodium, you're in essence holding down a spring with your thumb. What happens the minute you stop holding the spring down with your thumb? Boing! You get to make sound effects, guys. Boing! Come on. Boing! It immediately comes unsprung. The minute you stop holding down that electron onto sodium, that electron just, it pops off. You can't hold it in place. This is a case where the energy here is 10 and the energy here is 100. The difference is plus 90. Again, remember, these numbers are all made up. They're just to illustrate the point. This is a positive electron affinity. Ain't gonna work. Absolutely will not work. It's not stable. Anything that has a positive electron affinity basically cannot be made to hold on to an extra electron. It won't take it. So this would also be a little bit, if I shrink this down, well, actually, let me just do this. If we imagined sodium, just regular old sodium here, it's bad enough sodium hasn't yet gotten rid of its electron. How terrible would it be if it had to take another electron? It'd be ridiculously unstable. A sodium 1 minus, no, that's stupid. Won't work. It's like giving me raisins. It's not going to happen. Ugh. I'll probably throw them back at you. Ugh. They're just offensive on every level. You can't make it take it. Hey, I like that. You can't make it take it. It won't work. Positive EA atoms are totally unstable. Now, let me ask you one more question, then we'll finish. Okay, so here we have fluorine. Here we have a fluorine ion, fluorine 1 minus. It took on that extra electron. What would that tend to do to its radius? Jot down your answer and compare notes with a friend. So when we make an anion, in other words, what happens to the radius relative to the neutral atom from which it came? So, well, it would be reasonable to say, well, hey, the nucleus can get a better grip on that extra electron in the outer layer. And that seems like a good and compelling argument. What we do see is that the radius of this anion is going to slightly increase over its neutral counterpart because it is an uneven tug of war. So what we now have, despite the fact that it probably, no, ionization energy would, yeah, we don't talk about that. It would be easier to strip that electron off because it's, again, an uneven tug of war. Despite the fact that we've added one to the outer ring, so your whole traction argument, like, well, it's got more to grip, is good, it's still so now unevenly matched that you've got 9 people on one side of the tug of war and 10 on the other. So those 10 are going to be able to pull out a little bit. So anion formation actually does increase radius slightly. I mean, it's minor. It's a minor increase, but it does change the radius a little bit. Yes, sir? Because we deal in a lot of metaphors here. So the thought that, well, you know, if we use that tug of war metaphor, maybe the nucleus, you know, sort of gets pulled out. There's basically more forces in general on it. And that's true. The distinction is that the thing that changes atomic radii is really the electron cloud itself. The nucleus doesn't tend to change a whole lot until we add a lot more protons and neutrons. So yeah, that's one of the downfalls, and I've read about this in some science education journals. Like, one of the downfalls of analogies is sometimes if you follow them through to their complete logical conclusion, they kind of break down. So like we tend to pick and choose a little bit. But yeah, you're right. You're right. I can see that. But in general, when we make an anion, when we make a negative ion, the radius of the negative ion is slightly larger than the radius of the neutral atom that it came from. Okay, quickly do the example that was your quiz problem that I told you to skip because it was about anion radius versus regular radius. So let me give you 4 choices. Okay, so we've got boron. No, I don't like that. Don't like that a bit. Let me fix that. Let me make that fluorine. So I've got still don't like that. Let's do this. Lithium, beryllium. We'll stick beryllium and boron in there. Lithium, beryllium, boron, fluorine, and the fluoride ion. Put them in order from largest to smallest. So decreasing order of size. Somebody give me their largest thing here. What's the biggest thing in this lineup? Even if you don't, you know, just thinking about the elements, period. You got one, Sydney? What do you think? You afraid to commit? Okay. Did you compare notes? You don't have anybody at your island. Jaden. Fluoride ion, you say, is the largest thing there. It's an awful big plus or minus sign. Okay. Anybody in agreement? Anybody else got that? Explain your logic on that. I like it. I'll say right off. I like it. Okay, so we know then that the fluoride ion would be larger than what, for sure? Okay, larger than the regular fluoride. So we have one relationship here. I'm going to move these to the middle. Now, in a period, and these are all in the same period, where do we find our largest atomic radius? Okay, so group 1. So in this period, what would be the largest thing overall? What would have the largest radius overall? Lithium. So your logic was sterling on the fluoride ion, and it is larger than the fluorine but the fluorine tends to be on the small end. So I'm going to move that over there. Now, if we know that fluorine is going to have the smallest radius in its period, and lithium is going to have the largest radius in its period, is it an easy matter now to put in the puzzle pieces in the middle? Yeah, because now we're just going in descending order. And, you know, geez Louise, who wrote this thing? I actually wrote them in almost order. That was stupid. What we know about the ion is it's going to be a little bit bigger than its corresponding neutral atom. Does that make sense? We good? Okay. You'll probably have a question like this on the test. The test will be very much like the quizzes. Trends in EA, and that's about it. So atoms, you know, the halogens suck up electrons like nobody's business. And EA tends to become more negative. EA in group 1 and 2 is actually positive. They're not stable. They can't hold an extra electron. They want to get rid of the one they have. They're not taking another one. So that's what we got. Questions, comments? I'll add a few homework problems, and I'll probably give you most of tomorrow to work.